Hello everyone. Let's define orthogonal complement of an orthogonal complement. Let S be any non-empty subset of a Hilbert space H, then orthogonal complement of S, or we can say S perp. Perp is the abbreviation for perpendicular, is a subspace of H. We define orthogonal complement of S, or written as S perp by the set containing the vectors of H such that inner product of x comma y is equal to 0 for every y in S perp. Now we can prove these elementary results. Orthogonal complement of the singleton set containing 0 vector is H. Orthogonal complement of H is equal to the singleton set containing 0. Third one is S intersection S perp is equal to the singleton set containing 0 vector, and S1 is contained in S2 implies S2 perp is contained in S1 perp. Okay. Now we have a theorem. If M is a linear subspace of a Hilbert space H, show that M is closed if and only if M is equal to M perp. Now let's prove the theorem. By the definition of M perp, we can write x belongs to H such that inner product of x comma y is equal to 0 for every y in M perp. Now in the first part we assume M is equal to M perp, and to prove M is closed. Now we know that if M is a subspace of H, then M perp is a closed subspace of H. Similarly, if M perp is a subspace of H, then M perp is again closed. But we have assumed that M is equal to M perp. Therefore, M is closed. Now, conversely, we assume let M be closed, and to prove M is equal to M perp. Now, by the definition of M perp, it is x belongs to H such that inner product of x comma y is equal to 0 for every y in M. Now, x belongs to M implies inner product of x comma y is equal to 0 for every y in M perp, and from 1 we can see that x belongs to M perp. Therefore, x belongs to M implies x belongs to M perp. This implies M is contained in M perp. Now, to prove that M is equal to M perp, we have to prove that M perp is also contained in M. Now, suppose this relation is proper. Let us suppose that the relation 2 is proper, so that m is not equal to m per perp. Now, if we assume that M is a proper subspace of M per perp, then we know that there exists a non-zero vector Z0 in M per perp such that Z0 will be perpendicular to M. Since M is a proper subspace of a Hilbert space M per perp, then there exists a non-zero vector Z0 in M per perp such that Z0 is perpendicular to M. Here Z0 is not in M. Now, if Z0 is perpendicular to M, then this implies Z0 belongs to M perp, and here we have assumed that Z0 belongs to M per perp and also Z0 belongs to M perp. So therefore Z0 M perp and Z0 belongs to M per perp. Therefore Z0 is in their intersection. But we know that their intersection is the singleton set containing zero vector. Therefore, 0 Z0 must be equal to a zero vector. So, we got a contradiction that Z0 is non-zero. Contradiction for Z0 is non-zero. Therefore, hence M must be equal to M per perp. Okay. Now, let's move to the next theorem. Let's prove this theorem. If M and N are closed linear subspaces of a Hilbert space H such that M is perpendicular to N, then M plus N is also closed. Let Z be a limit point of M plus N. Now, to prove that M plus N is closed, it is sufficient to prove that this limit point belongs to M plus N. To prove that M plus N is closed, it is sufficient to prove that sufficient to show that Z belongs to M plus N. Right? Now, if Z be a limit point of m plus n, then there exists a sequence Zn in m plus n such that limit Zn is equal to Z. Okay, so now we have assumed Z as a limit point of m plus n, and now to show that m plus n is closed, we have to prove Z belongs to m plus n. Now it is also given that m is perpendicular to n. M is perpendicular to n implies M intersection n is the singleton set containing 0 vector, and therefore the linear sum m plus n is nothing but the direct sum of m plus n, because their intersection is the singleton set containing 0 vector. So this implies there exist unique elements xn in m and yn in n such that Zn is equal to xn plus yn. Right? Now norm of Zn minus Zn is norm of xm plus ym minus xm minus yn, or this can be written as norm xm minus xn plus ym minus yn. Okay, now xm and xn are the elements of m, and ym and yn are the elements of n. Then we can prove that xm minus xn belongs to m and ym minus yn belongs to n. Now m and n are orthogonal to each other, therefore xm minus xn is orthogonal to ym minus yn. Now by the Pythagorean theorem, we have norm xm minus xn plus ym minus yn squared is equal to norm xm minus xn squared plus norm ym minus yn squared. Right? Now from here it is norm of Zm minus Zn. So this can be replaced by norm Zn minus Zn. So it is norm Zm minus Zn squared is equal to norm xm minus xn squared plus norm ym minus yn squared. Right? Now we know that Zn is a convergent sequence. So this implies this sequence is a Cauchy sequence, and therefore if Zn is a Cauchy sequence, then norm of Zm minus Zn tends to 0 as m comma n tend to infinity. Okay, now from third we can write norm xm minus xn squared plus norm ym minus yn squared tends to 0 as m comma n tend to infinity. Now from here we can write norm xm minus xn squared tend to 0 and norm ym minus yn tends to 0 as m comma n tend to infinity, or we can say norm xm minus xn goes to 0 and norm ym minus yn to 0 as m comma n tend to infinity. Now from here we see that the sequences xn and yn are also Cauchy sequence. Xn in m and yn in n are Cauchy sequences, and since M and N are the closed subspaces of a Hilbert space H and H is complete, therefore M and N are also complete, and therefore every Cauchy sequence in M or N is convergent to some point in M or N. Since M and N are closed subspaces of H, which is complete, therefore M and N are also complete, and hence every Cauchy sequence in M or N is convergent to some point in M or N. Okay, so now let X belongs to M and Y belongs to N such that limit xn is equal to x and tends to infinity, and limit yn is equal to y and tends to infinity. Right? Now from 1 we can write z is equal to limit of zn, and zn is equal to xn plus yn. Therefore it is limit of xn plus limit of yn, and we can replace limit of xn by x and limit of yn by y. So it is x plus y, and x belongs to m, y belongs to n. So x plus y belongs to m plus n, right? So finally z belongs to m plus n, and therefore m plus n is closed. So if z be a limit point of m plus n, then we have proved that m plus n is z belongs to m plus n, therefore m plus n is closed. Okay, now let's prove an important theorem known as projection theorem. So it's an important theorem known as projection theorem. If M is a closed linear subspace of a Hilbert space H, then H is the direct sum of M and M perp. We know that if M is a closed subspace of H, then M perp is also closed subspace of H. We know that if M is a closed subspace of H, then M perp is also a closed subspace of H. We have already proved it. Now M intersection M perp is equal to the set containing 0 vector only. Therefore, to prove that implies H is M plus M perp and M intersection M perp is the set containing 0 vector only. So now it remains to show that H is equal to M plus M perp. We know that M and M perp are the closed subspaces of H. Therefore, M plus M perp is contained in H. Okay, now it remains to show that H is contained in M plus M perp. Now let, if possible, H is not contained in M plus M perp. Then we can assume it as 1. then the relation 1 is a proper relation, that is M plus M perp is a proper subspace of H. M plus M perp is a proper subspace of H. Therefore, we know that, we have already proved it, we know that there exists a non-zero vector Z0 in H such that Z0 is perpendicular to M plus M perpendicular. Here Z0 does not belong to M plus M perp. Okay, so now this implies Z0 is perpendicular to M and Z0 is perpendicular to M perp, or we can write Z0 belongs to M perp and Z0 belongs to M perp, or this can be written as Z0 belongs to their intersection and it is the set containing 0 vector only. Therefore, from here we see that Z0 is a 0 vector, but again it's a contradiction because Z0 is non-zero, so it's a contradiction. For Z0 as non-zero vector. Therefore, we must have H is contained in M plus M perp. Right? So, combining 1 and 2, we get H is equal to M plus M perpendicular, or we can say that H is the direct sum of M and M perp, since M intersection M perp is a 0 vector. Okay, so it's proved. That's all for this lecture.